Good morning, I'm Manuel Zarzo, and in this Unit 7 about ANOVA, I'm going to explain an application of ANOVA, which is design of experiments. This is important in research, and every time that we carry out an experimental design, ANOVA is the method that we will apply to analyze the data. Okay, so what is an experiment? An experiment is like a set of trials that we carry out to obtain information in order to improve a product or process or to obtain useful information about something. Okay, so a common approach that is used to optimize industrial processes is the following. Usually, there are processes that are very complex. So there are different things that we can do, like we can change the temperature in different steps, we can change the pressure, or we can change the catalyst, or we can change the type of something, okay? And then there are so many things that we can change to improve the quality or to improve the yield that many times the technicians or the engineers responsible of the process don't know exactly what to do. And then when some kind of experiment is decided to be carried out, quite often what they do is like to select the first factor that is considered like probably the most important. So they run like some trials with this factor at a lower level, which I represent here with this minus sign, and then some trials are carried out at a higher level, which I represent here with this plus sign. Then imagine that we carry out, and the rest of the factors are kept like the same level. I mean the common level or the ordinary level that is used in that process. So then imagine that based on the response, we analyze the response, and then we obtain that working with the factor A at the higher level is better than working with the factor A at the lower level. Okay, so this is useful information that is obtained, and so the engineers can say, so from now on we will work with those new conditions. So that's good. So now in the second step they say, well, now we have optimized one factor, so from now on we will work with this factor like at the higher level. For example, temperature, they have increased slightly the temperature. Okay, so now they select or they choose a second factor which is considered like potentially important, and then they make the some trials at a lower level than usual, and other trials at a higher level than usual, and the rest of the factors constant. So they run out the trials and then they obtain the result, and then imagine that in this case a higher value or a better response is obtained when the factor B was at the higher level. Okay, so then this is like a good information. So the engineers decide that they will work a factor at the higher level, factor B also at the higher level. And then they choose a third factor, and some trials are carried out with C at a lower level and other trials with C at a higher level. So this experiment is carried out and then we obtain response. Then imagine then that we get that when the factor C was at the higher level, we get a better response, okay? And then we finish the experiment. So the total number of experimental trials in this case was 24. And so the answer was that the optimum operative condition obtained was the 3 factors at a higher level than usual. Okay, but is it actually the best condition? Actually no, because not all possible combinations have been tested, and actually this approach is not efficient. This approach is called modify one factor at a time. It's not efficient. It's very expensive because it requires many trials, and also it does not guarantee obtaining the optimum operative conditions, and also it's not possible to study the effect of the interaction. So the approach that is recommended because it's more efficient, okay, is a factorial experimental design. Okay, it's very useful and very convenient when we want to study the simultaneous effects of different factors. So in this case, with 3 factors at 2 levels, this would be the best option. The best option would be to test A at lower level and higher level, so minus plus, B the same, minus plus, and C. Okay, in this case, the 8 different combinations are tested, okay, and then all the possible combinations have been tested in this experiment, and then only 8 trials are necessary compared with the 4 trials in the traditional approach. So this approach is much more effective. And also, the effects are orthogonal, and it's possible to study the effect of the interaction. So this is a new concept that I will explain. The effects are orthogonal if we work in this way. Okay, so what are controlled factors? The control factors here is the set of parameters of the process that are tested at 2 or more levels or variants in order to investigate the effect over the response variable. Okay, for example, it could be like a temperature, pressure, pH, type of raw material, type of catalyst, or whatever. Okay, so if the factor is qualitative, we call variance, for example, to work at 2 or 3 variants. But if the factor is quantitative, we usually call it levels. So we will say 1 quantitative factors at 2 levels or 3 levels. Okay, although the difference between level and variance, the concept is basically the same. Okay, so now imagine that we have a DOE, a design of experiment with 3 factors. F1 with 2 variants, like the 2 type of catalyst, F2 at 2 levels, imagine that pressure equal 2, pressure equal 3, and F3 at 2 variants, for example, 2 types of suppliers. So imagine that we run out this experiment, and imagine that this is the experimental result that we get. Okay, this is the response variable, which is measured experimentally. Okay, so the treatment is the different combinations of variants or levels. Okay, in this case, the first factor had 2, which is multiplied by 2, which is multiplied by 2. So here we have 8 combinations. So we have 8 treatments. So repetitions or replicates is the number of times that each treatment is tested. Well, in the design of experiment, the concept of repetition or replicate is not exactly the same. Okay, so it can be like more or less defined a bit more accurately, and you can find in some places that it can be like slightly different. But here, the subject, to simplify, I'm going to assume that it's the same concept. Okay, and the trials. So the trials is the number of assays that we carry out. So it's number of treatments multiplied by the number of repetitions. In this case, we have 8 treatments, but just 1. Okay, so because we don't have replicates, so 8 values in total. Okay, so we will say that this is a factorial design, not replicated. It has 8 treatments and 8 trials. So you can see that this slide contains like the definition of the different concepts that we will use in the design of our experiment. So another concept is when we say balanced factorial design. It is when all treatments are tested at the same number of times. Okay, so if this value is 1, so we will say a non-replicated factorial design, as in the previous example. Okay. Well, one property of this kind of designs is that all factors and interactions are orthogonal among them. Okay, and now I will explain this concept of orthogonality, which is very important. Okay, so steps to design an experiment. So first, we have to identify the response variable that we have to measure. It can be time, it can be weight, it can be any kind of physical magnitude that we can measure. Then we have to select the factors and decide the levels or variance for every kind of these factors. Then we have to decide the number of trials. Obviously, the higher number of trials, the higher the information that we get from our experiment, but also it will be more expensive and more time consuming. Also, we have to decide the treatment for every trial, and then we will carry out the experiment, and then we have to analyze the results with ANOVA, which is the more powerful technique for this kind of experimental designs. And then one important thing, very important, every time that we carry out a design of experiment, is that the trials should always be carried out in a random order. So in the design matrix that I have shown in the previous slides, it was like arranged quite clearly, but actually we should never carry out the designs in such a structured way. We should randomize the order of the trials in order to avoid the confusion of effects with uncontrolled factors. Okay, this is a concept that I will explain in the next slides. Confusion of effects. Okay, why? Because there are also factors that we cannot control and that may be present, and the only way to avoid this problem, which is a very important problem in the design of an experiment, is to carry out the trials in a random order. Okay, so for the analysis of results, first we will identify with ANOVA which effects are statistically significant, the simple effects, and also the effects of the interaction. Then we have to interpret the nature of the significance effect. What does it mean? Well, so if we have factors which are qualitative and we have more than 2 variants, okay, so if we reject the null hypothesis, remember that we don't know exactly where the differences, in which variants we have differences, so we will have to use L as the intervals to better discuss this issue. But if factors are quantitative and they are tested at more than 2 levels, okay, the best method is multiple linear regression in order to discuss if we have linear effects or if we have a quadratic effects, which is like a curve. Okay, then another step is the analysis of residuals. This is important to detect outliers or to study the normality of the data, which is one of the hypotheses of ANOVA, and also to study the effects of factors over the variance of the response variable, which is the hypothesis of homoscedasticity. Remember that we are assuming that all the populations have the same variance, and this is a hypothesis that we have to check at the end. Okay, so what happens when we have factors at 3 levels? 3 levels, they provide more information. Okay, of course, if we have factors at 2 levels, so the number of trials is less, so the experiment is easier, is not so much expensive, it's less time consuming. But if we have factors at 3 levels, we need more trials, but it provides more information about the linear or quadratic effects, which is important. So if we have one effect that we suspect that may have a quadratic effect, like a curve, something like this, so it's better to work with factor at 3 levels. So it allows a better estimation of the optimum. Okay, good. So the data analysis with ANOVA implies 3 assumptions. So one is, as I was explaining before, homoscedasticity. The populations corresponding to all tested treatments have all of them the same variance. Okay. Anyway, what happens if this hypothesis is not accomplished? So it's not a major problem. Usually they say that ANOVA is quite robust, though variances are not all equal. Another hypothesis is normality. Okay, so it means that all populations are normal, so the response variable has a normal distribution in all the treatments, okay. What happens if this hypothesis is not accomplished and if we have skewed, for example, positively skewed distributions? So we can use transformations. So, for example, in the case of right skewed distribution of the residuals, we can apply transformations like the square root or the 4th root or the logarithm instead of working with the original values. And this is a way to overcome this problem. And also the third hypothesis is independence. Okay, actually it's the most important. So it means that observations from its treatment correspond to individuals randomly extracted from the population considered. It means that if I have one trial and then have another trial, okay, so the value that I have in one trial is independent from the values that I obtained in the previous trials. It's accomplished in most cases, but not always. And if that is the case, so if if the hypothesis of independence is not accomplished, it can be an important problem. Okay. To accomplish this hypothesis, it's necessary to randomize the order of all trials in the experiment. Okay, so this is very important so that this hypothesis more or less is accomplished. Okay, so here we finish this video about the concepts of design of experiments. Thank you.